Welcome back. In this video, we are going to focus a little bit more on the plotting capabilities which are offered by Pandas. We are introducing a new library called Seaborn, which is specifically suited towards visualization of statistical analysis. So as usual, we have the default plotting library, which is Matplotlib. Note that Pandas and Seaborn are both just wrappers around Matplotlib. So essentially, without Matplotlib, these two libraries won't work. In order to exploit the visualization capabilities of Pandas or of Seaborn, you still need Matplotlib. Matplotlib is like a low-level library which allows you to play with every single element of a chart, whereas Seaborn is something that works at a very high level in the sense that it is very much aware of the kind of analysis and the kind of data that you're already giving it, and it creates a lot of assumptions on what sort of data you're giving it, and therefore draws a chart. Now, the chart that Seaborn creates, you can use Matplotlib to sort of tweak it and change some of its attributes. What those attributes are and how you essentially keep on changing a chart, tweaking a chart to make it look better is what this particular video is about. So as usual, let's run the imports, and there we are. Now in this particular notebook, we are going to look at a new data set, which is a data set from a fictional supermarket. And it has the details of all the orders that have been placed with that store, and a bunch of other details related to each order. So we are going to, as usual, read the file with the read CSV function. This is the location to the file. And note that here we are using a new parameter that is used in the read CSV function, which is called parse dates. Essentially, what this means is that we have two columns in our data set, which are called order date and ship date. Now, these are date columns. What parse dates is going to do is that it's going to take this list and it's going to parse these particular columns into date time objects. So it's essentially going to convert those columns not as text but as date time objects. And that's useful because datetime objects have a lot of interesting characteristics, like you can directly extract things like the year, the month, the day of the week, hour, minute, seconds, and so on. Whereas if it was actually just present in text, then you would have to do a lot of text or string manipulation on that. And that is not required when you have those columns parsed as datetime objects. And then we have another column called order ID, which is just the unique ID of each order. It doesn't really help us much in this case, so we're just going to delete that. And then let's look at the data set. So let's run this. So here is what we have. We have the order date, the ship date. Each row is particularly one specific order that was placed. And there is a ship mode, which can be second class, first class, standard class, and so on. There is a customer name, there is a segment. Then the segment is basically the segment, the market segment to which that particular product belongs. The city in which the order was placed. The region is basically the south, north, east, and west region of the United States. The category to which that order belongs. So basically, the first three orders are furniture orders, specifically bookcases, chairs, and tables. And the second two orders are office supplies, which are storage and paper. And then the sales is basically how much sales the store made on that in dollars or whatever currency. And the quantity is basically how many quantities were shipped, how much discount in percentage was offered for that particular order, and what is the absolute profit in dollars that the store made. So these are our columns. So what we're going to do simply is, well, one of the most important things that people would like to know about this sort of a data set is what were their yearly sales. So let's say that we simply want to take the year information from these dates and add up all the sales to see what the yearly sales are. One quick way to do that is simply take the order date column, and when you access the .dt attribute of the order date column, that gives you the underlying date object here. So essentially, if you just look at, say, df order date, you'll see that it has a date time 64 data type. And if you were to actually get the dt attribute of it, that is basically going to give us access to the date time properties of it. And then when I do a dot year, I get the years, which is 2016 for the first two rows, then 2015, and then 17 for the fourth row. I can also do something like month. So it tells me that the first two orders were placed in August, the second two were placed in November, and the fourth one was placed in April, and so on. I can also look at the day. So basically, the first two orders were placed on the 11th of the month, the second on the 10th of the month, the second and third on the 10th of the month, and the fifth on the 15th of the month. So I can use this sort of a thing to access any sort of an attribute of a date time object. So let's take a look at what we're doing with that over here. Let's say that we do df order date.dt.year, which is basically the year part of this particular value, and that we are going to assign to a new column called year. So basically, let's just do that. And then what we are going to do is we are going to group the whole data by the year. We have seen a group by operation before. What it's going to do is take each unique value, which is in year, and it's going to take the sales column, which is this column, and it's going to sum up that column for each year. So that's what it looks like. So for the year 2015, this is the sum of all the sales that that store made. For 2016, it's this value, and for 2017, it's this value. We can almost see that it's almost completely incremental, it's increasing, right? So here's a few types of charts which we can use to represent this data. Well, the first and foremost, one of the things that we have seen is a bar chart. We already have this variable, this yearly sales data present in a Panda series. We can just say xdf.plot kind equal to bar, and there it is. Now you see that we have three bars, one for each year, one for 2015, one for 16, and one for 17, and they are increasing, which basically means that my annual sales are increasing as the years go by. Now, of course, you see that in this particular chart, I know that 2015 is a little above 400,000 and a little below halfway between 400,000 and 500,000. So just by looking at this, it's not very easy to say what is the exact value or what is the closest round number to which this height matches. So in order to change that, I can simply add a grid attribute to it. So I can do something like this, and that gives me a grid. So you see that now I have the vertical and horizontal lines, and I can just say that this one is higher than 6,000. Now, of course, it may be obvious in this case what the values are, but when the charts grow bigger and larger, and when these x and y axis, when they grow in scale, it doesn't become very obvious, and therefore it might be useful to introduce a grid. The other aspect of this chart is that so you can see that it's built up of three rectangles, and they can have their own colors and transparencies. So let's say that I want to do a plot, but this time with a green color instead of the default blue, and I want to make it transparent. So basically I can do something like this. So you see that now I'm seeing things in green, but my transparency is 20%. So this alpha is a parameter which helps us control the transparency of each color that shows up in the chart, and the color is a parameter which tells us which lets us control what color we want to plot the chart in. So I can convert it into red, and I can say change the alpha to 0.5, and that gives me a semi-transparent red color. Now of course, if I set alpha all the way to 1, which means that it's completely opaque, it's not transparent at all, in that case this is what it would look like, right? So there we are. This is how you can control the colors and the transparencies of multiple colors. So the major reason why you have to use transparencies is because sometimes you might have overlapping objects in your data, and if you have solid colors, then some objects might get completely overlapped by something that is above them. So that is why you can adjust the transparencies so that both objects, even if they are overlapping, are suitably visible. Then of course, let's add a grid over here, as we have seen already. So these are basically the types of charts. Bar charts is there, and the next type of charts is line charts. Essentially, this is wrong. This should be line charts. Yeah, we have already seen what a bar chart is. Now the other type of chart is a line chart. Now actually, if you think about it, it's basically the same information which is being plotted in different ways, but you see how different it looks and how unusable this line chart is. If you look at my x-axis, you have things all the way from 2015, 2015.25, which is, I don't know, 3 months, 1 quarter into the year. Then there is 2016, 2016.25, 2016.5, all the way up to 2017. So this is not readable at all. And essentially, if we just have 3 values in the x-axis and a bunch of values on the y-axis, it's just going to draw a straight line. So you see that a straight line is not very suitable when you have very few data points to draw. In this case, we have actually only 3 data points. So when you have a very small number of data points to draw, and especially if the values on the x-axis are categorical values, then we might not want to use a line chart. However, there are a bunch of different things that you can change even with the line chart. So for example, one major thing that we see wrong with this particular plot is that the x-axis ticks, these labels that you see here, these are called the ticks. They are not at all readable. If we look at XDF, we see that there are only 3 values, 2015, 16, 17, but we are seeing all of these 0.25, 0.5, 0.75 intermediate values in them. So I could simply want to change these to reflect only these 3 values and nothing else. So when I draw the plots, I can do a set x ticks, which is set the ticks on the x-axis to the index of XDF. Now the index of XDF is 2015, 2016 and 2017. When I do that, I get the same chart, but this time my x-axis tick labels are a lot more readable. They are certainly not as cluttered and as confusing as this is, right? Then another thing we can also do is that we can take a look at the labels and titles of this image. Now I know that I have year on the y-axis, on the x-axis. I have no clue what is there on the y-axis. It's just some number that I'm seeing, right? So in order to make it self-explanatory, I can add something like a set y label, which will say that these are my sales, and they are indeed our sales because that's the analysis that we have done. And I can also add a complete title to the whole chart, something that appears at the top which says that this is yearly sales. So let's run that. By using set y label, we have created this title, this label over here, sales. Now earlier we had label only for the x-axis, now we have one for the y-axis as well, and we have added a title for the entire chart, which is yearly sales. So for that we used the set title function. There are a bunch of different line styles that we have used, so that we can use. We see that this particular line is a solid straight line. We can have a dashed line also. So here's a dashed line. Similarly, we can also have a dotted line, and that's a dotted line. We can also have a dash dot line, which is basically a mix of these two options. So that's how it looks like. You see a series of dashes and dots. And whenever you call the plot function, the default chart that it's going to draw is going to be a line chart, unless you see that we provided a specific parameter which says kind equal to bar. It's only then that it's going to draw a bar chart or a pie chart or any other kind of chart. By default, it will always draw a line chart, and you can have a parameter called line style, which can be dashed, it can be dotted, it can be dash dot, which lets you pick a particular style of the line that you want to draw. Now you can also adjust the color and the width of the line. So you see that this is the default width of the line. You can simply say that I want my line to be 10 pixels wide. So for that, I can use an argument called line width, and I want to say that my color needs to be red. And when I run this, you see that my line is a lot thicker. The width of my line is now 10 pixels instead of the 1 or 2 pixels that was over here. I have a line that was fairly large, and now it's colored in red. I can also compositionally add the line style attribute to it. So I can say something like line style is dotted, or it is dashed, or it is dash dotted. Oops, sorry, that's a typo, and there we are. So you see that all of these attributes you can mix and match to come up with the right kind of, exactly the right kind of graphic that you really want. So all of them more or less work independent of each other. For example, the line style has nothing to do with the color, and the color has nothing to do with the line width, and the line width has nothing to do with the line style. So they are all mutually independent. However, note that this particular combination of attributes will only work with line charts. They may not necessarily work with bar charts. I can try a line width over here. Basically, if I want to shrink the width of my rectangle, so let's try that. That doesn't work. You see, it just stays the same. I can't also use a line style because this is not a line chart essentially. So there is no, oh sorry, that shouldn't be a 5. That should be something like dashed. And you see that also that doesn't work because that's simply not an attribute which applies to a bar chart. Color does apply to a bar chart. So I can have a green color, or Yeah, so I can have a green color, I can have transparency. So you see it's now green, but a little more transparent. And here also, transparency is something that you can say applies to this. So I can write something like this over here. So you see that it's a very transparent red line over here. So many of these attributes will apply to many of the charts, but you can't just add any attribute to any chart and expect it to work. So be careful about that. But however, note that you can always look at the documentation of Matplotlib or Pandas to figure out what are the options you want, and therefore figure out what sort of parameters you want to set to come up with the right kind of chart. The second most important types of charts that we are going to look at is heat maps. Now, the yearly sales, line charts and bar charts that we saw here, again, they are reflective of univariate analysis. But when we go over to bivariate analysis, we have to look at heat maps and scatter plots. So let's look at heat maps first. So let's say that we want to basically create cross tabulation of the category and the region and put the values as sales. So what we are doing is, we are going to say that if you go all the way back to our data, we have something called a category, which is furniture, office supplies, and something else. And then we have a state or a region. So for each category and region pair, what are the total profits? So that's exactly what we mean by a cross tabulation. So let's try that. We are essentially saying that cross tabulate the categories against the regions and sum up the sales. So we are saying that create a new data frame where the index or the rows are going to be categories, the columns are going to be the region, and the values are going to be the sales, such that they are summed for that category and that region. So let's see how that looks actually. Before we actually draw the heat map, let's simply see how the cross-tabulated data looks. So this is how it looks like. So basically for furniture that was sold in the central region, these were the sales. For office supplies that were sold in central region, these were the sales. And for technology products that were sold in the central region, these were the sales. And that same thing applies to the east, south, and west region. Now you see, this is just a rectangular grid of numbers. One easy way to simply visualize this is to use something called a heat map. And heat maps come from Seaborn, which we have imported as SNS. So let's try that. There we are. So we see that there is basically a grid of colors in front of us. Each value is basically an intensity of that color. So this looks like a heat map. Whichever has higher values will be redder, and whichever has lower values will basically, or rather high value, you can see that there is a color scale over here. So I can look at the scale and figure out what these values mean. So essentially office supplies in the south are very low because they're at the lower end of the color scale. At the same time in south overall, it seems like the sales are pretty low, and technology in the east is very high. It's way over $200,000. That makes sense. On the East Coast, there are a bunch of technology specific businesses, right? So that is what a heat map is. It essentially plots a two-dimensional grid of numbers with colors so that you can see a heat map. And we have these four regions and we have these three categories. Now, just like bar charts have thickness and bar charts have colors and transparencies, line charts have line styles and line colors and x-axis labels, y-axis labels, ticks, and so on. Heat maps also have their own elements. The most important element of a heat map is the color map. So this is one particular color scheme that we are using. We can use multiple other color schemes. So this is a scheme called blues. When we use that, we get everything in shades of blue. So we see that very high values are over here, which is technology in the east, just as we saw over here. And we have very low values for office supplies in the south, which again you can check by looking at the color legend bar over here. Note that color maps are very useful when presenting to an audience. There may be people who are in fact color blind in your audience, and you might have to consider picking heat maps that are, or rather color schemes that are suitable for anybody's viewing. At the same time, depending on what sort of a projector you have or what sort of a medium you are using to plot your charts, you might have to pick the right color map. For example, if I wanted to use this particular thing so that, if I wanted to send this to a newspaper, then I probably wouldn't use this color map. I'll probably use something like a gray color map. So that might actually work out better in the case of a black and white newspaper, say. I can also have a greens color map, which gives me something like this. So there are a bunch of color maps. The default one that we usually use is Viridis. So I think it's a small v. Yeah. So this is also one of the most famous color maps that Matplotlib uses. You can use and pick the right color map depending on who your audience is, where you are going to be plotting this, and if it is meant for consumption outside the Jupyter Notebook. And then of course there are cell annotations. Now what I'm doing with this is that I'm looking at the color of a particular cell. Let's say I pick a region, I pick a category, I look at a particular color, and then I look at this scale to see what closely matches that color. Now, if I'm not very careful, I can easily go wrong. For example, I don't know if there is a difference of shade between this color and this color. I have to be very careful while looking at this, and most people in your audience are not going to be that careful. So one quick way to deal with this is to show values right in the box itself. So we can do it something like this. So we have a blue color map, and the values that are basically the sales of a particular category versus a particular region are printed right in this box straight away, right? But these are printed in the exponential notation. I want to see the exact value. So I can use a particular format. The G format is basically just going to turn this into an integer. And the annotate equal to true format is basically going to annotate each box with the value. So when I run this formatting, I get the exact integers out. And I see that not only does my color help me find out the higher and lower values, the value actually tells me what the real value is. And that's useful because then the density of the color, or basically the hue or the intensity of the color, it serves the purpose of drawing my attention to a particular box. But when I actually want to look inside that box, I can just read the value. So both our problems are solved in this sort of thing. However, you can realize that this works only because it's a 3 by 4 matrix. We have only 12 values. What if you have something which is 10 by 10 or 20 by 20 or even larger? There it may not always work. There it wouldn't suffice to simply print out all the values. There you're probably better off simply looking at the colors, because if your heat map is large, then you simply cannot print color values inside each or you can't print numerical values inside each single box. There's just not enough space to do that. The next thing that we need to figure out is the scatter plot. So Seaborn also gives us a scatter plot. As you remember, scatter plots are the easiest graphical way of doing bivariate analysis when both the variables are continuous variables. So let's say that on the x-axis we want to plot the quantity. Let's take a look at our data frame once again. That's our data. We have something called quantity, which is the number of products shipped, and the discount. So the idea would be that if I order multiple quantities of the same product in bulk, I should get some sort of a discount. So let's see if that is true. And when we do that, we see that there is absolutely no correlation. For all types of quantities, we are seeing that all types of discounts are present. So basically, items that have been ordered twice at a time, they have discounts which go all the way from 0% to 80%. So this doesn't make sense at all. The assumption that higher quantities lead to higher discounts is just false. And what this simply means is that there is no correlation between discount and quantity, right? So this is, although it's a disappointing scatter plot, but nevertheless it is a scatter plot. It's a scatter plot that doesn't show any linear trend or anything like that, but nevertheless it is a scatter plot. We can maybe also try something what would you have it? So let's say I have quantity versus sales, and there it is. So this is a slightly more meaningful scatter plot, because we see that the sales for quantity also are fairly random. You have quantities that have been ordered once, which make very little business, but at the same time you have quantities that say at the level of 5, where if you order 5 products at a time, it may make sales anywhere from 0 to 175 $70,500, but that seems to be an outlier. This again seems to be an outlier. So you can use this kind of a technique to figure out correlation between 2-3 things. Just like heat maps, bar charts, and line charts before it, scatter plots also have their own attributes. One of the most important attributes of a scatter plot is something called a hue or a density. So let's go back to the quantity and discount scatter plot that we had earlier, and we say that we want to hue it, that is, we want to color it by the profit. And we give it the data and we say that we want to use the blue color scheme. So there it is. So you see that now we have the same scatter plot, but the color of each plot can be changed according to how much profit that particular order has made. So we see that most of these orders are making almost zero profit. There are some which are slightly darker, some which are very light. So we have profits between 0 to minus 5,000, which is basically just straight up loss. But then, this is one way where you can add one other dimension, the quantity being one dimension, the discount being another dimension, and the profit being the third dimension. But since it's a two-dimensional plot, we don't have a third axis here to show the profit. So we encode the profit in the color of each marker separately. Let's try and change the profit to something like sales. You see, here we have a fairly different plot in the sense that almost most of the plots have gone away and you can see some dark spots here and there. So you see, you can use the hue to encode a third element of information as well. Then you can also change the marker style and sizes. So here the marker style was basically a circle which was blue colored. You can also change the size. So basically I can say that my X is quantity, Y is discount, U I have already, the color that is, I've already used that to encode the profit. I can quantify the size by sales. So let's see that this is what we get. You see that there are some bigger circles and there are some smaller circles. Those are basically something that, denote the size of the sale that you have made. So larger circle means a larger sale, and the darker circle means how much more profit you made. So now here we have a way of encoding 4 different types of information, just like compared to the 3 before. Here we have 4 types of information. We have the quantity, we have the discount, we have the profit, and we have the sales. Quantity is represented by its offset on the x-axis, discount is represented by its offset on the y-axis, profit is represented by the hue or the darkness of the color, and sales is represented by the size of the bubble. So you see that this here is a bigger bubble than this particular bubble, which means that this particular order made a larger sale than this one. So now we have gone from representing only 2 types of information to representing 4 types of information using different visual elements that are present within the same plot. This is something that you can keep on configuring endlessly just by changing X, Y, hue, and size to different columns of the data set, and therefore coming up with better and better plots until you have the right size. Of course, here we had size as a function of one of the columns present. You can also have it fixed. So say I want to keep it fixed and I just want every plot, every dot to look the same way. So there it is. We basically have every single circle with the same size, no matter what its attributes are. The only thing that it shows us is basically the hue, X, and Y. So the quantity, discount, and profit are the only things we can infer from it, but the size is fixed. I can also change the marker style itself. So these are all squares. I can convert them into stars. So I can look at this like that. I can convert them into pluses, which would make it appear as crosses. Of course, this is not at all readable. Even stars are not completely readable, but you can pick and choose the right kind of thing to show the different kinds of things. So let's say that I would want to use stars for furniture sales versus dots or circles for technology sales versus for office supplies. I want to use something like, diamonds or something like that. So yeah, something like that. I can use that as well. So here again, you have ways of using markers to encode or represent categorical data. So just like you have X and Y representing numerical data, hue or sizes representing numerical data, you can use markers to represent categorical data as well. So let's say I use a different marker for a different category of sale. That's perfectly valid. The idea is that you are able to encode different types of information in different visual elements of the same chart. That's broadly how we do effective data visualization with Python.